Okay, where we started talking, or where we left off last time, was we were just about to start talking about reactions that are known as ionic reactions, and that is reactions between ionic substances that are soluble in water. And so those ionic substances would be termed aqueous ionic substances, and if they're both soluble, they can combine with each other and form various products. In order for them to react with each other, you usually, but not always, need the reactants to be soluble in water. And in any case where an ionic compound is soluble in water, it's actually going to be present as separate ions, not as the intact substance that the molecular formula implies. So if you write NaCl in water, you can call it NaCl aqueous, but it'll really be present as Na plus aqueous plus Cl minus aqueous. The two ions will separate and essentially go their own way. And so that's the way they really are. The way that equations are usually written, or the way that we've written them so far, is known as the molecular equation. And it's called molecular equation because the reactants and products are all written as if they were present as intact molecules. Of course, like I just said, in the case of soluble ionic substances, writing them as if they were intact molecules is not really accurate. It's not really the way they are in solution. But for many purposes, it's close enough. It can get the idea across of what's going on. And as long as you know the background and you know what's really going on, and for most purposes, the molecular equation is perfectly adequate. But we're going to have a deeper look at what's really going on in the solution by writing different types of equations for ionic reactions. So if you have, for instance, a reaction of sodium chloride dissolved in water with silver nitrate dissolved in water, the result will be basically an exchange of cations and anions. So for sodium chloride, you have sodium is the cation, chloride is the anion. For silver nitrate, silver is the anion, and the nitrate ion silver is the cation, nitrate ion is the anion, and they basically switch partners. So what you get out is sodium nitrate, that is sodium comes out with nitrate, and silver comes out with chloride. But as it turns out, silver chloride is not soluble in water. So we write that as AgCl with an S after it for solid. And that would be our molecular equation for this reaction. But as I said before, NaCl dissolved in water is really present as Na plus Cl minus ions, two separate ions. Silver nitrate is really going to be present as Ag plus NO3 minus. And here's where it's really valuable to be able to recognize polyatomic ions when you see them. So the NO3 ion itself will come apart from the silver because that's an ionic bond between the silver and the nitrate ion. But the bond within the nitrate ion between the nitrogen and the oxygens, that is not an ionic bond because nitrogen and oxygen are both nonmetals. And so that is a covalent bond, and it will not be affected by water. Very rarely are covalent bonds affected by water. And so the NO3 part will remain together as the polyatomic ion NO3 minus. And so that's the way silver nitrate is really present in water. Sodium nitrate is also ionic and soluble in water, so that will really be present as Na plus ions and NO3 minus ions. But the AgCl, silver chloride, is not soluble in water, so it really is present as intact AgCl molecules. And we write that as AgCl solid. With that information, you can actually write a more accurate depiction of what's really going on in the solution, known as the complete ionic equation. And that just involves the substances being written as they really are in solution. So if NaCl is actually present as Na plus Cl minus, that's the way you write it. And at AgNO3 is actually present as Ag plus NO3 minus, so that's the way you write it. NaNO3 is actually present as Na plus NO3 minus, so again, that's the way you write it. But AgCl is actually present as AgCl solid, so again, that's the way you write it. And this is the complete ionic equation. If you go through this equation item by item, you may notice that some things change and some things don't change. Looking at you, sodium. Notice the Na plus ions, Na plus aqueous ions, come out as Na plus aqueous ions. So there's been no change there. And so you can kind of cross those out. You can basically say, nothing is happening here, and we want to focus on things that are changing because that's what the reaction actually is. And so we may not be concerned about the fact that there are also some sodium ions sitting in there. And also at the same time, you'll notice that the NO3 minus ions come out exactly the same as they went in also. So we might not be concerned about that because they didn't change. What we really want to focus on in most cases is what actually changes, because again, that's what the chemical reaction actually is. So you have Ag plus ions coming together with Cl minus ions to form AgCl solid. The ions that don't change are known as spectator ions because they're, well, you can think of it as just really sitting around watching the other ions react. And that's the spectator ions that we can cancel out if we want to focus on what's really changing. And when we do that, what we get is known as the net ionic equation. So the sodium ions are not changing, so we can ignore them. The chloride ions are changing because they go in as Cl minus, they come out as part of AgCl. That's a change, so we have to keep those. Ag plus ions come out as part of AgCl again, so that's a change. We have to keep those. But the NO3 minus ions come out exactly as they came, as they went in as NO3 minus ions. So those are spectator ions, and we can get rid of those. The result is the net ionic equation, which is Ag plus ions plus Cl minus ions yield AgCl. I changed the order of the two reactants so that they match the order in which they come in the compound. And that's okay. It normally doesn't matter what order you list reactants or products in a reaction. So you can do that. So that is the net ionic equation. That brings us down to the essence of what's actually happening in this situation. And it's also the most universal form of the reaction, because what it does is it tells you that anytime you get Ag plus ions and Cl minus ions together in solution at the same time, they will come together to form AgCl. And it doesn't matter where the Ag plus ions came from. They could have come from silver nitrate, but they could come from any soluble silver containing compound. And the Cl minus ions can come from any soluble chloride containing compound. As long as you can get Ag plus ions and Cl minus ions in solution at the same time, they will form AgCl. And that's why it's nice to know what the net ionic equation is, because it really sort of broadens things, opens things up. An example of actually writing molecular ionic and net ionic equations would be, say, for example, what if we want to write those three equations for the reaction of sulfuric acid and sodium hydroxide to form sodium sulfate and water. Sulfuric acid has the formula H2SO4, and sodium hydroxide has the formula NaOH. Sodium sulfate, well, sulfate ion has a -2 charge, so it'll take 2 sodium ions because each of them has a charge of +1. It'll take 2 of those to cancel out the -2 on the sulfate ion. So Na2SO4 is the sodium sulfate formula. And then water is, of course, H2O. But for balancing purposes, it might be more useful to think of water as HOH. You know, that's what water really is. When we draw a water molecule, we draw it as HOH. We condense that into H2O by putting the hydrogens together just for convenience, but it's really HOH. Or in other words, hydrogen hydroxide. And thinking of it as hydrogen hydroxide could make it much easier to balance equations that involve the hydroxide ion. So I'm going to think of water as hydrogen hydroxide. First thing we have to do is make sure the reaction is balanced, and this one is not. So there are no there are no elements by themselves. So it's not obvious what we need to leave for last. And in cases like that, you usually just go left to right. So hydrogens, now you have to watch here though, because this is hydrogens outside of hydroxide ions. So the hydrogens other than the ones in hydroxide ions, you've got two of them. Well, over here you've got one H2O. That means only one hydrogen that's not part of a hydroxide ion. So we need two H2Os to balance the hydrogens that are not in hydroxide ions. So that's why the 2 goes in front of the H2O. Then we can look at sulfate ions, because polyatomic ions normally don't break up in aqueous solutions. You can often balance polyatomic ions as a unit as long as that polyatomic ion is present on both sides. So if we see sulfate ions here and we see sulfate ions there, it's probably safe to balance the sulfate ions as a whole instead of balancing the sulfur and the oxygen separately. So we've got one sulfate ion as part of H2SO4 on the left, and one sulfate ion as part of Na2SO4 on the right. So they're balanced. That's good. For the sodium, we've got one on the left and two on the right. So that's why we end up having to have 2 in front of the NaOH when we balance the reaction. Putting the 2 in front of NaOH also changes the number of hydroxide ions, but that's okay because we have 2 H2Os, which means we have 2 hydroxide ions plus 2 hydrogens that are not part of hydroxide ions. So 2 hydroxides, 2 hydroxides. Now it's balanced. Now that we've balanced it, we can find the ionic equation by looking at each reactant and each product in turn and writing them as they really are in solution. If they're really present as separate ions in solution, then that's the way we write them. If they're actually present as intact molecules, then that's the way we write them. H2SO4 is a strong acid, and that means that it will actually ionize. The hydrogens will ionize from the sulfate ion, but it's important to remember that the sulfate ion itself remains intact. So you get the 2 H plus ions going one way and the SO4 minus 2 ion going the other way. So that's how we write it. NaOH is an ionic compound because you have a metal and a polyatomic ion bonded to each other. And that is soluble in water. So it will actually be present as 2 Na plus 2 OH minus. You got to remember that the 2 applies to the entire formula. So not only does it mean 2 sodium ions, it means 2 hydroxide ions also. For the Na2SO4, that is a soluble ionic compound because you've got a metal and a polyatomic ion. And so you'll have the 2 sodium ions coming off the main molecule. And remember, when the 2 sodium ions are part of the larger molecule, you use a subscript to indicate that there are 2 sodium ions involved. But when the sodium ions come off the molecule and they become free and independent of the molecule, then that 2 becomes a coefficient, like the 2's in front on the H2SO4. So it's 2 Na plus. That 2, though, that was a subscript originally, it only applies to the sodiums, not to the sulfate ions. So there's one SO4 minus 2 ion. And then there are the 2 H2Os. Remember, water is obviously soluble in water, but it's not ionic, so it does not ionize. So you write it as H2O, liquid, not aqueous. Aqueous water would be a little redundant. So aqueous tends to mean that it's dissolved in water, but water is water. So you don't write water aqueous, you write water liquid. The net ionic equation is what you get when you cancel out the spectator ions And the spectator ions are the ions that don't change during the reaction. The two H plus ions come out as part of H2O, so they have to stay. That's a change. The sulfate ion, though, comes out as a sulfate ion. Exactly the same. That's no change. Nothing's happening to it. That makes it a spectator ion. So we can cancel that out. The sodium ions, again, come out as sodium ions, and there are two of them in each case. So you can cancel both of them out on each side. On the other hand, the two hydroxide ions are part of the H2Os when they come out as the product. That's a change, so they have to stay. So your net ionic equation ends up being 2H plus 2OH minus yields 2H2O. But remember, I said when you're writing balanced chemical equations, you want to end up with the lowest whole number ratio of the coefficients. And so you may notice in this case, 2 and 2 and 2 can all be divided by 2. So you'd want to do that. And you end up with H plus OH minus yields H2O. That would be your net ionic equation for this reaction. It's, again, the most universal expression of this reaction. What it tells you is any time that you have H plus ions and OH minus ions in water at the same time, they will come together to form more water. And also this ends up being the net ionic reaction for any combination of strong acid and strong base. In this case, it was the strong acid sulfuric acid and the strong base sodium hydroxide. You could mix together any two strong acids and strong bases and end up with the same net ionic reaction. So that's why that's nice to know. Finally, reaching the second section of the chapter, we're going to look at some types of chemical reactions or classifications of chemical reactions. There are literally millions and millions of chemical reactions known, and so it can be helpful if you can sort of group them together in some way. Sometimes we group them together according to what the reactants are, sometimes according to what the products are, sometimes we group them together according to what happens during the reaction. So there are different ways of of classifying reactions, and the result is that there are some specific reactions that can qualify as more than one type at the same time. And so don't need to be too surprised if that happens. First, looking at precipitation reactions. Precipitation reactions are the types of reactions, well, we've actually already seen one, the reaction that produced the silver chloride. Because a precipitation reaction is a reaction where the reactants are soluble, but at least one of the products is insoluble. So we had soluble sodium chloride and soluble silver nitrate producing soluble sodium nitrate and insoluble silver chloride. And the fact that silver chloride drops out of solution as a solid makes the silver chloride what's known as the precipitate, because it comes precipitating out of solution. It kind of looks like snow falling out of the sky, precipitation. And so that's called a precipitate. So precipitation reactions usually involve soluble ionic reactants. And effectively what the reactants do is they trade the positive and negative ions in the reactants trade partners. And so a good way of looking at it would be sort of a general way of looking at it would be if you have a reaction where A and B are cations and X and Y are anions, and you start with the combination AX plus BY, you end up with the combination AY plus BX. So the ions have just switched partners. Forming a solid that's not soluble in solution is an example of removing ions from solution. And that is what's known as a driving force for this type of reaction. And essentially, in order to make the reaction go forward, you need some way of changing something permanently so that it won't just go back the way it was. So in this case, we've got, for precipitation reactions, we'll have a couple of ions that come together and basically get stuck together and won't come apart again. and they form a solid which falls out of solution. And because there's no easy way to reverse that, and it's certainly not going to reverse on its own, that would be considered a driving force for a reaction, or in other words, reactions like that actually do occur. There are a couple other ways of removing ions from solution. You could form H2O, which is the driving force for the reaction of the acid and base that we just looked at. One of the products is H2O, which does not ionize in solution. And so even though the H2O is still dissolved in solution, it's not dissolved as ions. And so in that sense, those ions have been removed from solution. And that is your driving force for that reaction. But that's not a precipitation reaction because the H2O is soluble in water. It's not a precipitate. Another way of driving a reaction forward by removing ions would be if the reaction produces a gas. The gas would bubble out into the room and it would literally be removed from solution. And so any reaction that produces a gas will be a reaction that actually occurs. If none of that stuff occurs, then what you probably have in most cases is just a bunch of ions sitting around waiting for somebody to do something, and nobody ever does. And in that case, there is no reaction. It's just a bunch of ions sitting in water. But anyway, back to precipitation reactions, where forming a solid that's not soluble in water is the driving force. Okay, reactions of this type, where the positive and negative ions of the reactants just switch partners, would be known also as double displacement or metathesis reactions. It's double displacement because you could look at it as basically both of the anions are being displaced and exchanged with the other compound's anion. And these are used in gravimetric analysis, which we will eventually do in lab. And I believe there are some gravimetric analyses a little later in this chapter also. This brings us to solubility, because in order to tell if you're going to have ions removed from solution as precipitates, you need to know whether the products are soluble in water or not. And that's what solubility is about. So solubility can be thought of as the extent to which a substance dissolves in water. And that would be the, also it could be considered solubility as the maximum concentration of a substance possible in a given amount of water under specified conditions. Solubility can be affected by things like temperature and pressure. Temperature affects the solubility of just about everything one way or the other. And pressure will have an effect whenever gases are involved. But we don't do a lot of gas-involved reactions in this chapter, so we don't have to worry about that right away. If the solubility of a substance is above a certain level, then it's considered soluble in water, or S as an abbreviation. If the solubility is below a certain level, then the solubility, then it would be considered insoluble, or I as an abbreviation. And if it's on the borderline, then it might be considered slightly soluble, or SS as an abbreviation. Let's see. If you try to dissolve a solute in a solvent beyond its solubility limit, then what normally happens is the excess amount of the solute will precipitate out of solution as a solid, or as a precipitate, or PPT as an abbreviation. Every substance that's soluble in water, well, just about everyone, has a limit of solubility. So even though, like, for instance, salt, sodium chloride, is really soluble in water, there is a limit to how much sodium chloride you can dissolve in water. And that limit varies a little bit with temperature, but actually even changing the temperature doesn't change the solubility very much. And so it is entirely possible that you could try to dissolve so much salt in the water that some of the salt just won't dissolve and it comes precipitating out as solid sodium chloride on the bottom of the container. That is possible. And the process would be known as precipitation. There is a table of solubilities on page 183, in the textbook, where it lists out various types of compounds. In most cases, it lists them out according to the anion that's present in the compound. And there are certain compounds involving certain anions, like say nitrates ion or acetate ion, that are always soluble in water, no matter what the cation is. And so those will basically be listed as soluble with no exceptions. And then there are certain other anions, like say the chloride ion, where most of its compounds are soluble in water, but there are a few exceptions, like for instance, silver chloride. And so they'll be listed as soluble, but then in the exceptions section, you'll have things like silver chloride and lead chloride and a few others that are not soluble in water. So the exceptions go in the opposite direction. And then in the bottom half of the table, you have basically you have the anions whose compounds are usually insoluble, like phosphate ions or carbonate ions. And so they will basically be any compound involving a carbonate ion is probably insoluble with some exceptions. And so exceptions might be like sodium carbonate is soluble, or sodium phosphate is soluble. As it turns out, all of the compounds that involve the metals in group 1A, they're all soluble, no matter what the negative ion is. So even if it's like sodium phosphate or sodium carbonate, it's soluble. But a vast majority of phosphate and carbonate compounds are not soluble. So if you take something like copper carbonate or silver, or basically calcium carbonate, say calcium carbonate or copper carbonate or calcium phosphate or copper phosphate, they're not soluble. But sodium with anything will always be soluble. Potassium with anything will always be soluble. Also, the ammonium ion with anything will always be soluble. And also in the negative ions, the nitrate ion and the acetate ion are always soluble, even if it's like lead nitrate or silver acetate, those will be soluble. So that table is very useful in deciding whether you've got a precipitation reaction happening or no reaction at all. An example where there is a reaction would be the combination of, say, lead nitrate and sodium sulfate. And although usually it's usually safe to assume that the reactants are soluble in water, and it may even be indicated for you by the little AQ after the formula, you could use the table to determine whether they're soluble or not. For lead nitrate, you can look for the nitrate ion on the table, and the nitrate ion will be in the top part of the table, and it will say that all nitrate compounds are always soluble in water with no exceptions, and so therefore lead nitrate must be soluble. It'll say that sulfate compounds are usually soluble in water with a few exceptions, but sodium nitrate is not one of the exceptions, and so sodium nitrate is soluble. Also, as I just said, all sodium compounds are always soluble anyway. For the products are what you get if you switch partners with the ions. So lead nitrate and sodium sulfate would produce sodium nitrate and lead sulfate. So we look at lead sulfate. Look for the sulfate compounds in the table, and it says that sulfate compounds are usually soluble, but lead sulfate is one of the exceptions. So that is not soluble. That's your precipitant. And then the other compound is sodium nitrate. Again, it'll tell you that nitrate compounds are always soluble no matter what. So sodium nitrate is soluble. Also remember, all sodium compounds are soluble no matter what. So sodium nitrate is definitely soluble. And so we can look at the Ionic equation. where we have lead nitrate being a soluble ionic compound. You'll get lead ions from it. The lead ions have a charge of +2 because it took 2 NO3 minus ions to cancel out the charge on the lead ions. So they must be +2. And you get 2 NO3 minus ions. Remember, when the NO3 minus ions are part of the larger molecule, the fact that there are 2 of them is indicated by the subscript. But when they come off the molecule and become free and independent of each other and of the lead, then that 2 becomes a coefficient. And so that's 2 NO3 minus. And remember that the NO3 is a polyatomic ion, so the oxygen and the nitrogen remain together because that's a covalent bond. The sodium sulfate, you'll get 2 Na plus ions plus the sulfate ion. And from the lead sulfate, you'll get lead sulfate solid because that's the way it really is in solution. It's not soluble. And then the sodium nitrate, of course, will ionize. So you get 2 Na plus aqueous and 2 NO3 minus aqueous. Remember, the coefficient applies to everything in the formula. And when you come through and look for spectator ions, you'll see lead ions come out as part of lead sulfate. That's a change, so you can't cancel them out. But the 2 NO3 minus ions come out exactly the same as they went in. So they're spectator ions and they can be canceled. The same with the sodium ions. They come out as 2 Na plus, just like the way they went in. And in fact, sodium ions and nitrate ions will always be spectator ions in any reaction where they occur. Plus, you've got the sulfate ions, which come out as part of lead sulfate. So that's a change, they have to stay. So your net ionic equation will be lead ions plus sulfate ions yield lead sulfate. And what that means is that anytime you get lead ions and sulfate ions together in solution at the same time, they will produce lead sulfate. And it doesn't matter what compound the lead was originally in or what compound the sulfate ions were originally in, as long as those compounds are soluble in water, so you can get lead and sulfate ions free and able to react with each other, they will form lead sulfate. Okay, well, that's a little over time for the first segment of the video, so I'll stop it there and we'll come back in a moment.